Geometry. Night. Geometry. Okay. We need more geometry cheers too. Okay. Anyway, here's your 12-4 video questions you'll be asked to think about when you get back to class. Oh, there's a plane flying over. 12-4 is about spheres. And that would be the last shape we're going to talk about in 12.4. Or sorry, chapter 12. Notice it's so small here. I can actually fit the 12.5 notes on the same piece of paper. 12.4 is really only that stuff. Yeah, there's just two little formulas here. One for the surface area, one for the volume of the sphere. That's all we got. Why is this little thing following me around all the time? All right. So yeah, there's a couple formulas here to memorize, I suppose, about how to find these measurements on a sphere. This is 4/3 pi r cubed. You know what? Let me rewrite these in my handwriting. It might look a little bit nicer. All right, there's the questions again. Here's a nice picture of a sphere I found. Yeah, you're probably not going to deal with diameter very much. Of course, you know how to deal with diameter versus radius. That's no problem. Yeah, so surface area. Or you know what our book says? No, that's not what our book says. Our book says total area. Most books would say surface area. Equals 4 pi r squared. Now that looks really just too simple, actually, I think, for the surface area of a sphere. Surface area of a sphere seems really complicated. Seems like, oh my gosh, how do you actually flatten this thing out into some shape and find the area of it? Why does it look like 4 times some sort of area of a circle? It does. The formula looks exactly like that. It looks like 4 times the area of a circle, where this is the radius. Notice in this picture of a sphere, they show this thing called the great circle. Oh, by the way, what is a sphere in the first place? That's kind of important to know. Sphere is just like a circle in two-dimensional geometry. A circle is in one plane. It's all the points that are a certain distance away from a center. If you collect all the points at a given radius distance away, you find all of those points that meet that requirement being a certain exact distance away from a certain point. You will have populated a circle full of points. The sphere is exactly the same thing. It's all the points anywhere, like on, it looks like the horizon there, but anywhere on this sphere, whoops, kind of slipped there, that are the same distance away from this center point. If you can imagine that in 3 dimensions, that really doesn't look very good. But now we're talking about, but that's the thing, we're talking about 3-dimensional distance. So from this point hanging in space, any distance or any point that's exactly r away from that, so it could be coming straight out at you, but if it's exactly r away from the center, it belongs on the circle, and that's the entire bubble there. So that's the definition. All points a given distance are away from a center point. So I'm going to just start over, get rid of all my junk here. I didn't mean to get rid of that. Total area, 4 pi r squared. Why is it exactly 4 pi r squared? That pi r squared, if we're talking about the same radius as the radius of the sphere, you could think of that pi r squared is the area of this little flat thing in here. Like if I cut the sphere exactly in half and I have an exposed circle, that circle is the biggest such circle you could sort of expose when you take a cross section. That's called a great circle. Think of the equator of the Earth. It's the largest circle you can have on any sphere. You could also draw a circle up here, like if you had a rubber band on this circle and on the sphere, it could sort of sit around here as a circle maybe without flying off somehow. That's a circle on a sphere, but that's not a great circle. A great circle is a circle that goes around like an equator that has as its diameter also the diameter of the sphere. This one is not so great. Anyway, the area of that great circle is pi r squared, and what this formula is saying is that it takes 4 of those to cover the sphere, exactly 4, which seems like it's just too friendly. Well, it is, and actually the proof of that has nothing to do with the fact, it's just sort of a happy coincidence, that it takes 4 of these circles to cover the sphere exactly. Why is it exactly 4? Again, it has nothing to do with that circle directly. The proof of that actually is easier to prove once you know what the formula is for volume. Volume of a sphere is just this fraction, 4/3. Now we're starting to get messy. It's one of the messiest formulas in geometry. 4/3 pi r cubed. Now notice we have a cube version of r here and a square version of r here. That is sort of predicted because here we're talking about volume, so we have cubic meters, cubic inches, cubic centimeters. Here we have area, so it's square units, square inches, square centimeters. That should sort of make sense. 4/3 pi r cubed is a little bit easier to demonstrate. I'm going to have to do this in class, why it's exactly 4/3 pi r cubed. It's very cool. And again, once you sort of have established and can really believe in the 4/3 pi r cubed, then you can start to see why this surface area turns out to be 4 pi r squared. I don't like the way the book does that. I have what I think is an easier way to see on that. This also, the way the book does it, they compare, what they do is they compare this to another solid of a known volume, and you can say, well, if the cross sections of this are always equal to the cross sections of this other thing, then I know they have the same volume. And if I know this volume, I can figure out the volume of the sphere. And it turns out to be 4/3 pi r cubed. You don't have to, like lots of our proofs in this semester, you don't have to reconstruct why it is 4/3 pi r cubed. You're just supposed to believe me and do it. So, kinds of problems you're going to get. Here's a little sphere. Let me copy this for now in case I need to draw another one. Let's say we know, pretend this is the center of the sphere. It looks like I'm kind of drawing this on the sphere, but let's pretend I cut it open and this is the inside. So you know the radius is, I won't do that then. Let's say the radius is 8. Let's find the total area. And really there is no such thing as lateral area here. There's no walls that aren't really different from the whole thing. It's not like there's a floor and a ceiling we can take off the the total area called lateral. So there's no such thing as lateral. We just go straight to total. 4 times pi times r squared. No big deal. 64 times 4. Oh, can I do that in my head? I think I can. 256 pi. And that's in square units. Volume, just as easy, but not quite as nice numbers. 4/3 pi times that number cubed. Yeah, I think it's calculator time. Get my newer version of my calculator out here. 8 cubed, I don't actually know that off the top of my head. It's 512. So it's 4/3 times 512 times 4 divided by 3. I know this is going to be gross, but I want to make it a fraction. It's 2048 thirds pi. So that's the exact answer. If you want a decimal answer, you know what to do. You hit the pi button on either one of these, and you get a decimal. If this were inches, this would be square inches, because this is, after all, the surface area, and this would be a volume, so this label would be cubes. Okay, that's the most kind of straightforward problems you're going to get. Might be a little tricky to locate what the radius is, like if they give you diameter, or if they give you the circumference of a great circle, you'd have to, you know, use that to figure out what the radius is. That's not too bad. If they chop one in half and tell you what the flat area is, you could figure out the radius is not too bad. It starts to get a little bit weird if they give you, what if they tell you something like, well, the total area is 80 pi. Find r. And the question is, find r. Well, I know that the total area is 80 pi. 80 pi is supposed to equal the area, which is 4 pi r squared. You can fast forward if you know where this is going. Divide both sides by pi, divide both sides by 4. R is the square root of 20, which I don't like to leave that way. I like to bring that 4 out as a 2. I have 2 square root of 5. And you could get a decimal for that if you wanted to. Okay, there's a question like that in the do now. I suppose the most complicated version of just sort of a one question type thing. I mean, it gets more complicated. They're going to give some crazy stuff like, okay, there's this ice cream cone. You got a sphere kind of sitting in a cone, and they give you the radius of the cone, which might be different than the radius of the sphere, and they give you the height of the cone. They say if the ice cream melts, is it going to fit in the cone, that kind of stuff. So you got to do some comparison stuff. But really, when it gets down to it, volume of a sphere is about, you just got to know radius and put it in the formula. Surface area of a sphere, you just got to know radius and put it in the formula. And sometimes that's easier said than done, because of the way you have to go about finding radius. But the one that I think is going to be the most tricky is, what if they give you the volume? Say the volume is, let's make it a nice number. Well, let's put a pi on it just because this is the first time you've ever seen it. Say the volume is 200 pi. I'll make sure that's not actually the thing. And again, what's the radius? I guess this thing doesn't have to be this big. There's nothing I'm actually drawing on the diagram. I'm just reminding you that we're talking about a sphere. There's no reason why it has to be ominously huge. Okay, because I mean, I'm just doing this and saying, okay, there's a radius. It's a sphere. What is there to do? There's nothing to do. You just know that that's the volume. And that volume equals 4/3 pi r cubed, and I just have to solve that for r. The tricky part is I've got an r cubed, and eventually I'm going to have to solve for a cubing thing, and that's kind of new. Divide by pi. divide by 4. This little thing is not a fraction bar, it was just an underline. So now this is 50. So I got 50 equals r cubed over 3. I guess I can multiply both sides by 3. There we go. So r cubed is 150. Now the problem is, how do I figure out what number times itself is 150? You did this a little bit in the volume chapter or section on cubes, because sometimes it would say, okay, you know the volume of a cube. That's really where we're at now. I've got the volume of a cube whose edge is r and whose volume is 150. How do I figure what r is? I could drive myself crazy going guess and check, like 6 times 6 times 6. Oh, that's too big. 5 times 5 times 5. Oh, that's a little bit too small. It's somewhere between 5 and 6. Or I could just use the calculator to tell me, and that is in the math menu. This thing, the fourth thing down, is the cube root of. And I go cube root of 150. And actually, you know what? Cube root of 150 is as nice as we can get it. Oops, 150. Cube root of 150 is like sort of the exact answer for r. Oh, good question. Would you ever have to simplify this, pull out any cubes we know about? That would be mean. I don't know if I would do that to you or not. I don't think so. Any cubes go into 150? Oh, yeah, then you could pull them out. Like if 27 went into 150, I could pull out a 3. Or if 8 went into 150, I could pull out a 2. Does 8 go into 150? I don't think it does. 27 doesn't go in. Cubes get really big really fast. The next cube is 64. It doesn't go in. So none go in. So this is the most reduced. If you want it as a decimal, you do the thing in the calculator, and you get 5.31. Probably enough. I'll say it because I was looking at it. 5.313. Again, if this 200 pi were the volume, they'd have to give you this unit as something like, centimeters cubed. That would be the units on this thing. And if that were the case, this would then be in centimeters. And sometimes, I guess, if they're really mean, they'd say, okay, here's the volume. Actually find the total area. Well, there's no nice conversion from volume to total area without actually finding radius first. So you would just find radius and then stick it in here. So really, there's not a whole lot to do. Once you get to the sphere part of these problems, it's just about finding the radius and putting it into one of those two formulas, the 4/3 pi r cubed for volume and the 4 pi r squared for total area. This is the end of it in terms of exact. If I wanted to approximate, I would take this thing I had and, oh, you know what? Oh, wait, I was talking as I did that. That should be squared. I have it in the calculator. Let me square. That is the best way to write that exactly. The only way to proceed from here is to go into approximation land and square this and multiply it by 4 pi. And we get something like 354.76. Seems kind of inappropriate to do that, but because I started with a nice exact version, sort of 200 pi, it wasn't 628 point whatever. This would, of course, be in centimeters squared. This, I don't know if I'd make you do exact on this. I should talk to other teachers about if they're going to make you do exact on something with a cube root in it or even that. Probably not. Probably decimals. Cube roots and exacts is just getting a little bit too picky, I think. Okay, sorry I rambled on more than I thought I would. Really, for these two pretty easy formulas, I hope you fast forwarded if you needed to, because that's all there is to it. Until you start combining other shapes and making it hard to find r. The only new stuff here, though, is actually pretty easy. I will see you in class.